This is the last chapter that you will see before we start titrations for acid-base. And this is part 3, and we're going to discuss pretty much buffers in this reactions. And buffers are a type of common ion where we have a weak acid and its common ion which happens to be a salt of its conjugate base, okay? And or we're going to look at a weak base and its salt of the conjugate acid of that base. You're going to see examples of it. In this chapter, we're going to look at, first, I'm going to just review briefly the derivatization of the Henderson-Hasselbalch equation. I'm also going to do the common ion effect and show you some calculations with the common ion effect. And I'm going to do the common ion effect because I want you to understand the difference between the idea of a common ion and a buffer, which is hardly any different other than the concentrations perhaps, which have to be taken into account. And then we're going to look at what are buffers. We're going to look at the buffer capacity and how a buffer resists the change in pH. And finally, we're going to look at some examples of how to prepare a buffer solution. The Henderson-Hasselbalch equation is an equation that we will always use whenever we have a weak acid and its conjugate base salt, right? So if I have a salt, NaA, solid, of course, you all know that that splits up in water into Na plus and A minus. And if I have a weak acid, HA, you all know that HA will also react with water to give you, let's say, H3O plus and A minus. This is just simplification here, and we just put H plus and A minus. Nonetheless, the first reaction is a one-way reaction. The second one is a reversible reaction. And remember, when we have that type of a thing, we take the first reaction with it as if the A minus is already in my solution, and I take it into the second equation. And now, we're going to look at the examples of that. So if I have here an initial C0, my A initial, A minus, in my solution will be C0. And so here, not only will I have some HA in my solution, I will always have as well A minus, which is also equal to that upper amount. So the A minus will be C0 in my solution. Thus, whenever I calculate Ka now, I actually already have some HA and I already have A minus. And that is why we can actually do this derivatization and do this type of reaction, because I have both HA and A minus, and thus I can solve for H plus. Solve for H plus. Take the minus log of both sides. If I take the minus log of both sides, this becomes simply pH equals pKa. And here, if I actually take the plus log, I can flip the two, the denominator and numerator, and I become plus log of A minus divided by HA, which is your typical Henderson-Hasselbalch equation. Now, when we put A minus and HA in this form, we mean A minus at equilibrium and HA at equilibrium, because of course, you know, the Ka expression are concentrations at equilibrium. Now, one of the biggest questions I used to ask myself, could we not use this for normal acid base, you know, weak acids and weak base? We can if we already know the A minus concentration, which in most cases we do not. That's an unknown. It's normally an X, because usually we don't have anything in solution. That's usually 0 initially, and then you say X and X as a product. All right, so that's simply pH equals pKa plus log of the conjugate base of my weak acid. When do I use this? Whenever I have a weak acid and its conjugate already inside my solution with some concentration. I could then automatically get the pH from the system. And you will see why I could automatically get the pH, even just knowing the initial concentrations when we do a calculation in a moment. All right, what else can I do with this Henderson-Hasselbalch equation? Well, you can derivatize, do a few other calculations, such as if I am given a pH of a system, what I can do is take the pH minus the pKa, okay, and take the antilog, and actually then I can get the ratio of my A minus to HA, which gives me that pH value. And this is a very important type of rearrangement of the Henderson-Hasselbalch. I could also then, if I have HA, I could calculate how much A minus I have in solution, or I should have in solution to give me that particular pH. So those are the equations that you will need in this type of, part, which is part 3. And you need to know those, the Henderson-Hasselbalch and its derivatization equations. Let's now get into the actual chapter. Okay, this is the common ion effect. And a common ion effect is a shift in an equilibrium, which is caused by the addition of a compound having an ion or a common ion with the actual dissolved substance. What do I mean by that? If I have already an acetic acid, okay, and I mix with it, let's say sodium acetate, you all know that sodium acetate is a strong electrolytic salt, so it splits up completely. And if I have acetic acid, the acetic acid will react with my base, which is water. Now, one of the questions is, why doesn't it react with this base? Because the acetate is actually the conjugate base of this acid. So this is not another base. If it were another base, we would have a mixture, acid-base mixture. This base is the same base of upon deprotonation of this proton. So this is not an acid-base reaction. This is a single acid reacting with water, always giving you H3O plus and the A minus. And this happens now to be a common ion because we have this A minus coming from two sources. It's coming from the acid dissociation and from the salt dissociation. Thus, we call it a common ion. And when we have that, what happens to this net equilibrium is that at equilibrium, not the K doesn't change, that just changes the Ka, doesn't change. That only is affected by temperature. However, what does change is the position of the equilibrium. We will no longer have as much products as we had before due to the presence of this common ion. And thus what happens is the reaction moves more backwards because I have some products already. Okay, so we have the presence of a common ion suppresses the ionization of weak acid or a weak base, and we're going to prove that to you by a calculation in the next example. So let's look at what is the pH of a 1 molar solution of acetic acid. Well, all of you already know acetic acid is a weak acid. I'm given the Ka. What can I do? Of course, you can write down an equation. You don't have to. Right away, ask yourself, is the concentration greater than 100 Ka? Yes, it is. It's a 1 molar solution. Look at the Ka. Definitely, it's greater than 100 Ka. Which equation do you use? You use pH equals half pKa minus half log C, or, take the half out. Log of C is 1 minus log of that number, add the pKa, divide everything by a half, gives you the pH. Okay, so my pH is 2.37, and all of you should get this in quick. No, you shouldn't have to think about it at all. If you want to check this, then you ask yourself, is this pH less than pKa minus 1? But of course, you don't need to do the check because you already started with this C is greater than 100 Ka. you already used the correct equation. Okay. What is the pH of the solution changed, or will the pH change, and how much? If I add now to the same solution 1 molar of acetate, sodium acetate. Now, when I say sodium acetate, usually it's a bit odd to add 1 molar since it's a salt. So when you add it, you really add mass, you know, you add grams. So this is after dilution or after dissolving this salt in my solution. So in other words, my volume is the same. This is already dissolved salt, okay? So yeah, you have to sometimes watch out for those things. The salt dissolves, you get the anion and the cation, and we're gonna see what is this effect. I'm gonna do it the long way, but then at the end, I want you just to simply use Henderson. Okay, or actually I'm gonna do it the short way first. Anytime you have a weak acid and a weak base, and you already know their concentration after mixing in my solution, okay, so their dilution, you already took into account, simply use Henderson. And instead of A minus and HA, use the initial concentrations of that material. CH, this is A minus initially and acetic acid initially. And I'm going to show you why I'm going to be allowed to do this. But this will be a very easy calculation. Your pH will simply equal to the pKa of the acid plus the, or of the couple, plus the log of the base concentration divided by the acid concentration after mixing. You could also use moles and moles because the volume would be the same. It happens to be 1 and 1, so pH is simply half pKa. Now let's prove to you and show you the long way. And one of the things I'm going to ask, you know, you never have to use the long way. You can simply use Henderson. But I want to show you the long way because I want you to understand what's actually going and what's happening in my solution. Well, of course, you have the acetic acid that's going to dissolve and dissociate and ionize in water into acid and acetate ion. You're going to have your ice table initial change at equilibrium, initial amount, 0 for water, and we already have in this solution an amount of acetate which is equal to 1 molar. That's an amount present in your solution. Great. Now change, minus x plus x plus x, voila, and now you have your equilibrium concentrations. What is different between this and what we had seen before? It's this common ion. Now it's a 1 plus x. Put the Ka expression, products divided by reactions, by reactants, substitute. So the Ka is 1.8 times 10 to the minus 5. This is going to be x for the H3O plus, 1 plus x for the acetate, and 1 minus x for the acetic acid. That's interesting because now I have plus x and minus x. What, do I have to really do a quadratic here, multiply everything out? That's a bit complicated. Well, I'll tell you one thing. If the x is not negligible relative to the 1 here, because 1 is my initial concentrations, yes, you will have to do a quadratic. But for the sake of this course this year, and you know, at least for now, we're going to assume, and I want you to always assume that this x is negligible. In other words, this x is less than 10% in the French system or less than 5% in the English system of my initial concentration. And since this is, you know, an acetic acid, normal acid mixture, we somehow can say, is the C0 here, the initial concentration, or the C, greater than 100 Ka? And in most cases, if that is the case, then this X is going to be negligible. Likewise, this is a base going backwards in a Kb type reaction. And so we ask here, is the initial concentration of the base greater than 100 kb? Then we allowed to neglect X. For you guys, always neglect the X, okay? But that is when we're allowed to neglect X. My assumption that that is the case. Of course, we can always do a calculation and see if X is negligible or if it's not. If I neglect my X relative to my initial concentrations or relative to my concentrations of solution of material in my solution, then X is canceled, and this is 1 and 1, so my X is simply 1.85, 1.8 times 10 to the minus 5. Take the minus log of the H3O plus to get pH, and you get pH is 4.74. Oh my God, look at all this that I did, and all I really had to do is use Henderson. Always simply use Henderson if you have an acid and a base in your solution, okay? Clear? But I did want to show you that indeed this type of system, this common ion type of system, does undergo an ice and a change. And if that X is negligible, then we simply apply Henderson-Hasselbalch. Clear? At initial concentration. So going backwards now, in my solution, which had acetic acid alone, I had a pH which was 2.37. And if I sit there and calculate how much H3O plus I have in my solution, it was going to be 4.26 times 10 to the minus 3. So if I'm asked for percent ionization for the acetic acid alone, it would be that acid concentration divided by C. And here, no, it's better to use the acid because that comes from my acid dissociation and not the A minus. Times 100, which gives me 0.426%. So percent ionization of the acid alone is this number, 0.4% approximately. However, combined, when I combined my acid with my conjugate base of the acid, or the salt of it, the pH comes out to be 4.74. Okay, so the pH increased upon adding the salt. Logically, because like we said, if I have less dissociation, okay, it means I don't have as much H3O plus in solution. That means I have a increase in pH, not a decrease. My percent ionization, look what happens to it. Of course, my H3O plus decreased. Therefore, what happens to the percent ionization? It also decreased. Oof, it decreased quite a bit. Now it's 1.8 times 10 to the minus 3%. So, and it's very logical that the percent ionization decreases. The amount of H plus in my solution decreases due to the Le Chatelier's principle. This guy is going backwards because I have already product, so this may go more in the back direction. Clear? So common ion effect decreases percent ionization, decreases the amount of H3O plus in solution. However, common ion of this sort increases my pH. A buffer. As you can see, there's a lot of writing on this slide, but it's just a bunch of introduction, blah, blah, blah. Of course, this blah, blah, blah is all about our bodies, and we're gonna say the following, that indeed our bodies operate in a very narrow pH scale. I can't sit there and have the pH of my blood 1 time 9 and 1 time 2, okay? That doesn't happen. The pH of our blood is maintained between 2.3 and 7.6. And our whole body is actually maintained between these two pHs. Outside this range, we will get respiratory malfunctioning, and all other organs as well will malfunction. cells will no longer function properly, and the proteins will actually start to break down. We might actually induce coma or even death to our cells, okay, outside this range. So whenever I take some Pepsi can and I drink Pepsi, or I inhale or ingest some acid or a base, definitely I do not, the worst case would be I would die. But of course, what happens is my body neutralizes whatever acid or base I take. And how does it do that? It uses what is called buffers. Okay, the buffer that is in our body is actually carbonic acid with the hydrogen carbonate ion. That's my weak acid, H2CO3. And my base is going to be HCO3 minus the conjugate base of that acid. It's this acid, weak acid, conjugate base. This is the buffer of my body. What do we mean by that? It means anytime I take in some acid, the HCO3 minus will come in and neutralize this acid, this H plus, and it will take it up. Anytime I take some OH minus into and ingest it into my body, my weak acid H2CO3 will neutralize that OH minus. And we're going to see exact calculations of how such neutralization takes place. And by doing this neutralization, that is how the buffer maintains its pH. Nonetheless, buffer systems are simple acid in the presence of its conjugate base, and therefore they are a form of common ion solution. Now, what is the difference between this common ion type solution and the one we just discussed? And that is the actual concentrations that we use, okay? In a buffer solution, whether we have a weak acid or its conjugate, or a base and its conjugate acid, again, we always have a weak base and its conjugate. These acids or bases have to be weak. And the reason they have to be weak is we need this equilibrium going on. And not only that, they should be the acid and the acid and its conjugate, or the base and its conjugate, should have very close range in concentration. So they don't have a wide range in concentration. And the reason for having a close range in concentration is so that they can buffer in the best way, and such that they will resist the change in pH only when their concentrations are not only close to each other, but also their concentration should be largish. We call it largish. A largish concentration means that usually the concentration is greater than 0.1. One of the reasons is remember that element of X being negligible in the common ion equation that I showed you, is that I want to keep that X negligible. So my concentrations, I really don't want to go too far beyond or below 100 Ka. I want to keep that concentration greater than 100 Ka. Right? And let's see how this acetic acid and acetate ion maintain pH. So if I ingest some H3O plus from an outside source, who do you think it will react with, first of all? Will it react with the acid, or will it react with the base, the conjugate of this acid? Of course, it's an H3O plus. An acid will not react with an acid, but an acid will react with the conjugate base. Not only will it react with it, we're always going to assume that since it is a strong acid, H3O plus, that the reaction goes first completely. And we neutralize all this H3O plus such that none of it is left in solution. So all the H3O plus effectively has been transformed into what? Into acetic acid. And of course, to be effectively neutralized, I have to have this base concentration greater than this acid concentration. Okay? Such that in the end, I'm still left with some base and some acid. And the closer that these guys are to each other, the better my buffering capacity, and we're going to look at that in a moment, will be. And of course, this reaction is quantitative, and it's treated as complete anytime we have a K reaction, which is greater than 10 to the 4. But I'm telling you from now, even if my K reaction is less than 10 to the 4, and I have H3O plus in solution, please treat it as complete. This is the K reaction, happens to be 1 divided by Ka, because if you look at the reaction, this is simply the Ka in the opposite side, and thus giving you this high K reaction. If I have a strong base now in my system and I ingest some strong base, who will he react with? With the acetate or the acetate ion or the acetic acid? Of course, a base will not react with a base, so the base will react with the acid. And now the AOH from my outside source, he will sit there and react with whatever acid I have in solution. And he will do this completely regardless of K reaction. Always OH minus, but again, if we look at the K reaction, this K reaction will be complete because this happens to be 1 divided by KB of my reaction, which is Ka divided by Kw, which since the Kw is so small, of course, this reaction will almost always be complete. Nonetheless, no matter what my Kb value, always, if I have a strong acid or a strong base, as a reactant, always treat this reaction going complete, one way. Thus, what happens to this OH? It will be completely neutralized, and all of it will be converted to the conjugate base of this acid when he reacts with the acid. Okay. Well, fine. Now, okay. So anytime I have H3O plus or OH minus, they will react completely and they will become converted. Okay. So what is a buffer capacity? A buffer capacity is the ability to resist any change in pH. So it's the ability to take up H3O plus and OH minus in a system. So of course I have to have some acid to take up the OH minus, and I have to have some base to take up the H3O plus. As well, the concentrations to be a good buffer should be largish. Okay, usually the acid and the base should be greater than 0.1 as a concentration. Lower concentrations can also, keep the pH constant, but not to the best of its ability. Okay? So we get lower ability if you decrease this concentration. As well, the concentration of the base divided by the concentration of the acid, the Cb divided by the Ca, is best when that ratio is between 0.1 and 10. Okay, so definitely should be, even the ratio itself should be greater than 0.1, and the ratio is best not to be greater than 10. Okay. When I have a buffering effect and I want to keep the pH constant, again, it's best to have a startup system or a system where the HA is equal or as close as possible to the A minus concentration. Because I want, in the end, if I use Henderson-Hasselbalch, I get a ratio, and I want to keep that ratio as much close to 1 such that my pH that I'm buffering at is closest to the pKa of my acid. The pKa value of the acid used in the buffer solution should be as close as possible to the desired pH. So if you had a choice in different acids, always choose a pKa of the acid closest to the buffer pH that you actually want to keep buffered. Okay, so we're going to look at, this is just a summary actually of what happens as a calculation-wise when we add any H plus or H minus into our system. And I take my original buffered solution, and remember, a buffer solution is simply a solution which has a weak acid and its conjugate base, salt, usually in the form of the salt, or a base and its conjugate acid. I take this original buffered solution, look at its concentration, and then I do first a stoichiometry, a complete reaction, a stoichiometric reaction, react it with the added H plus or OH minus, depending on what I'm adding. Do a complete reaction first, see what you have left over of the acid and the base originally, and then you don't have to really do an equilibrium calculation like the long extended way that we did initially. Simply apply Henderson, because in the new solution, we always also have an acid and a base, because it's best to keep this H plus and OH minus less than the acid and the base in your buffer. And finally, find the modified pH of your solution, of course, using the Henderson-Hasselbalch. And then here we have my HAX minus or HXX minus. If initially they are at the same concentration, if I add H plus, what happens is the H plus reacts with what? With the X minus. He gets removed completely. Who does the H plus material, what does it become? It becomes added HA, and you will see that the HA concentrations increases in my solution for my final system. If I add OH minus, who will the OH minus react with? He will react with HX, and my HX here will decrease in my system. And actually, not that the HX, indeed, it decreases and the X minus increases. But overall, the ratio between the two more or less remains the same. And we're going to see this. So here my X decreases, and here my H. And we're going to look at this by doing a direct application to an example, because of course an example really helps out. This is just a summary of if I have H plus, of course it will react with A minus, and if I have OH minus, of course it will react with the H plus of my system. If I have a BBH buffer type, the H plus will react with the base, and the OH minus will react with the acid of the weak base, weak acid mixture. Okay, we start with an example, and let's do that. We already calculated the pH of a common ion, and here I'm calling it a buffer system because it's really the same. Since the concentrations here are fairly high, you know, more or less, as long as I have an acid and its conjugate base, they will fit into a weak acid and its conjugate. They will fit into the idea of a good buffer. Okay. If I add to this buffer 0.1 mole of HCl, from now I'm telling you, if they don't give you this in moles, do calculate the amount of moles, okay? Because when you do a reaction, it's best to do a mole type chart. It's just easier. And when we get to titrations, you will see this quite a bit. Okay, so if I'm adding HCl, guys, I'm adding HCl. Of course, you all know that HCl is a strong acid by now, so that's H plus and Cl minus. Great. Now, if I have that strong acid, who will he react with? The H plus, of course, because Cl minus is useless, spectate. Doesn't react, doesn't do anything in my solution. What will the H plus do, or H3O plus? Who will he react with? Will he react with the acid of the buffer or the base of the buffer? Of course, he will react with the base of the buffer. Okay, so I will put a reaction, and we call this a stoichiometric reaction because we're gonna go to completion. We're gonna get everything out. We're gonna neutralize everything. The acetate will react with the H3O plus to become the acetic acid. If you put H3O here plus, you end up putting plus water on the other end. Same thing. What do I say? Initial moles. So if you have a volume, use the moles, okay? Multiply each of these by the volume. So here the volume, let's assume it's 1 liter, so the amount of moles is 1. Of course, your acid is also 1 initially. But as well, now I have H plus in my solution, so I put 0.1, which is the amount of moles. Notice that moles should always be less than the acid or the base in order to actually retain my buffering capacity. Because in the end, let's react. So who's the limiting reagent? It's of course the H plus. So that's going to become 0. So this is going to be 0 at the end. So how much reacted? Minus 0.01. I don't really need to put minus X because that's automatically the limiting amount. So it's going to be, the X will be minus 0.01. So put for this part minus minus 0.1. Put here minus 0.1 on the product side plus 0.1. Great, all my H plus has become 0. What happened in the end? Indeed, my A minus decreased, but my HA increased. The amount of acid in my solution, my weak acid, increased because all of the H plus became converted to this. What do I have in my new system, my new setup? I still have conjugate base and it's acid. Therefore, what is this? Absolutely, this is a buffer or a common ion type. And what do I use if I have an acid and its weak base? Of course. Do you have to set up an equilibrium and show the reaction or minus X or plus X? No, that's it. You simply use Henderson, pH equals pKa, the concentration of the base, whatever you have in solution divided by the acid. Do I really have to calculate concentration here? No, if I have moles in a moles chart, that's all I need. Just put the number of moles because the volume total is actually the same and they cancel out top and bottom because it's a ratio. And that's equal to 4.66. Clear? Great. Now, every year I regret showing this slide, but I can't help it, okay? If you want to, you ignore it completely, I don't mind, but just as a teacher, I can't help but to show you this slide, okay? And that is the following. You remember, okay, what actually happens is, once of course you could use Henderson, but I just want to show you again that the acetic acid in my system goes ahead after, here we have, that's it. Here we have a solution, we have acid and its base, okay? And the acid and its conjugate. What happens is the acid and a conjugate, of course, they react with water, right? In my normal dissociation. And we have a minus X plus X. Okay, and we still have H3O plus, but from where? Where is this H3O plus? Of course, it's from the acid dissociation. This H3O plus or this H plus is not what we had from the external source. That's now due to my acid base redissociating or re-reacting with water in the solution, okay? And I'm just gonna show you that all this is really, again, we could have used Henderson because Henderson is this acid dissociating in the presence of my common ion A minus in solution. So here is the molarity, the concentration of the acid and the concentration of the base after it already neutralized the H3O plus from the external source. So officially I have 0 H plus. But of course, this will undergo dissociation minus X plus X plus X on the product side, and we get a new equilibrium. And of course, we use the Ka to solve for the X of this new equilibrium reaction. Of course, what did we say? We assume that X here is negligible, okay, since this number is high, or that this number, initial concentration, is greater than 100 Ka or greater than 100 Kb. And thus, what happens is this 0.9 plus x is simply 0.9, and this 1.1 minus x is simply 1.1. And so I have simplified the equation. And then you solve for x. What's x? It's simply my H3O plus concentration. If you sit there and do this, solve for x, get the pH. What is my pH? 4.66. And you're like, doctor, why did you show this to us? We just solved this in the simplest way. And we said, anytime I have an acid and a base, simply use Henderson. And what pH did we get? 4.66. Now, why did I show you the other way? I'm just telling you where this pH is coming from, an H plus, right? Where is that H plus? It's not from here. It's not from this H plus. It's from afterwards, this acid and this base redissociated in water. Okay, I need you to understand that, because most of you have this concept as if there's some left over, H plus here. There's nothing left over. This is completely neutralized, nada, zilch, zero. Okay, great. But of course, none of you will ever do this, right? This is an X, never use it. This is long way just to show you, okay, you simply use Henderson. The minute you do a neutralization, complete neutralization of H plus, you have some acid, you have some base left, you do Henderson. Clear? Great. Now, hopefully students that end up seeing this lecture, you know, later on they're saying, oh, the doctor is speaking in such a long way and so complicated. Well, clearly they didn't hear the lecture, okay? I simply want to show you that the pH is this H plus due to the redissociation of the acid in the presence of the conjugate base. Great. A buffer solution, like we said, will always keep my pH more or less up and down a little bit, but more or less at a constant. However, if I have two solutions, a buffer solution and a water solution, and I'm adding slowly HCl, I'm adding moles of HCl to either water or buffer. Of course, you know that water, pure water, will start at a pH of 7. And as I add acid, what happens to the pH value? Of course, it's going to decrease. Okay, it's gonna decrease. It's gonna become more and more and more acidic. Okay. However, if I add moles of H plus to H plus, or which comes from a strong acid, right, to my buffer, what will happen? Nothing will happen. The pH will remain the same. It doesn't decrease. Why? Because again, that H plus from this external source is going to be picked up by the A minus and get converted into acetic acid. And then we have A minus acetic acid ratio that determines the pH from Henderson. Clear? Okay. Here's another final example of how our buffer resists pH. And now we're going to add OH minus to the system. So, but this here, we're going to look at. Calculate the pH of 0.3 molar ammonia with 0.36 ammonium chloride. So of course your ammonium chloride is simply ammonium and Cl minus, which is simply the ammonium in solution. Now you look at this ratio and you're like, doctor, it's not exactly the same. That's okay, but the range of these concentration and the ratio of the acid relative to the base, or the base relative to the acid, is within the range 0.1 and 10. So we're okay. It will form what is called a good buffering system, okay? Hopefully. Now, let's look first to calculate the pH without any addition of any external source, okay? Just the pH of this acid and base mixture. Okay, so yes, it is a type of mixture, or a common ion type of mixture, where we have the acid and of course you have the base already in the solution. Always It's like, why do I always put my acid on the, acid dissociation reaction? Because I'm using Henderson. And the way I'm using Henderson, we're always using it in terms of pKa. So it doesn't matter. You always, use the acid equation. Even if, we have more base or more acid, it doesn't matter. Okay? Of course, you don't need to set up an equilibrium, put initial and put minus x and plus x and set up the equilibrium and then do all the x calculation. No, we said as long as I have an acid and a base and its conjugate base in a solution, we call this common ion, or simply use Henderson, a buffer system, and use Henderson. Great. What do I use in Henderson? Of course, we have the pKa. We should have it. And we use the initial concentrations. You're going to ask me, is the initial concentrations equal to the concentrations at equilibrium, which this calculation is to be made? And we always assume that it is, that x is negligible. Great. That's it. And so the pH initially of my system is 9.17. Okay, if after I got a pH of my system and now I'm going to add some external source of 20 milliliters of 0.05 molar NaOH to 80 milliliters of my buffer. Okay, so actually I took a buffer because here it doesn't really matter in this equation what I had initially. How much I had of my buffer doesn't matter. But when I'm going to add NaOH, most of the time they give you a volume of the buffer and the volume of NaOH added, or any salt that's added, or any HCl that's added. What did we say? We said we should do a stoichiometric calculation, a complete reaction. We're going to neutralize all the what? The OH minus to get a new ratio of the base and the acid. So what do you start with? What equation? Well, depending on what I'm adding, guys. I'm adding OH minus. Who do you think the OH minus will react with? Will he react with the ammonium or will he react with the ammonia? Of course, this base, strong base, will react with the acid. Who's the acid? It's the NH4 plus. So the NH4 plus OH minus, complete reaction becomes the OH will become water and the NH4 plus will become NH3. Now, what concentrations do I use? I don't. I use moles. So I use moles, which is concentration times the volume. This is the concentration of the acid of my buffer times the volume. What is the volume? It's 80 milliliters. What is its concentration? Well, let's see. What do we have? It's 0.36. So 0.36 molar times, not 80, times 0.08. Because you have to multiply here by liters because it's concentration times liters. Find the moles. Okay. And what is the moles of OH minus? We're going to say it's simply CV because we leave it la acid la base. It's CV, which is concentration of it, which is 0.05 times 20 times 10 to the minus 3, or times 0.02. That gives me this moles. What is the concentration of water? Well, this here is now 0, but initially, of course, water is in excess. We don't ever look at it in my equations. What's the concentration of my base? It's CB times the volume of base. And we always, guys, when they tell you I have 80 milliliters of buffer, honestly, it doesn't mean that I have 80 milliliters of this ammonia and 80 milliliters of NH4 plus. No, I have a single solution which has the acid and the base mixture, and the volume of that solution is 80. And no, it doesn't mean that I divide this by 2, okay? It means that the volume of the acid or the base of the buffer is 80. Both have the same volume, and it's called the volume of the buffer. Okay, so you multiply those, concentration of, which is what, 0.3 times what? Times 80 times 10 to the minus 3 to get into liters. Okay, so yeah, you have the initial moles. What do you do now? Find the limiting reagent. Who's the limiting? Of course, it should be the OH minus. So that's going to become 0. Find the end moles. Okay, that's going to be 0. And we always put epsilon before 0. No one, you know, it's just a convention that we do. But officially, it's nothing is left over, or if there's anything from the back reaction, it's from the back reaction. Okay. What's left over here? 0.029 minus the limiting reagent 0.001, which happens to be 0.028. And what's going to be here? It's going to be plus the 0.001. And if you add that to 0.24, you get 0.025. What do I do now? Well, I should set up an equilibrium equation between the ammonia and the ammonium and the ammonia and find the X. No, we simply have acid and base in my mixture. What do? I use Henderson. pH equals pKa plus log of the base divided by acid. Do I actually have to go and get the concentration of the base and the concentration of the acid by taking the number of moles and dividing it by the total volume? Notice the total volume is 80 plus 20, which is 100, happens to be. Do I have to do that? No, guys, I don't. I simply take the number of moles that I got from this chart and divide it by the other moles, because V total is the same. So I don't really have to do the calculation of the concentration. I'm just showing it to you here so you see it. Equals the pH. What is the final pH of my new solution after neutralization of OH minus? It is 9.2. Well, look at the pH. Before I added any OH minus, my pH was 9.17. After I added OH minus, my pH is 9.2. And therefore, indeed, my pH is more or less the same. It hasn't changed much. I mean, imagine adding this OH minus concentration with volume to simple water. Your pH will be higher than this. Okay? Great.